We're now going to look at deletion when we're dealing with conflict resolution and linear probing. So basically, what about delete? How we do that? We use the search function to find the item, and if found at n, then what do? Could we just simply delete it, and then that's all we need to do? Well, let's remember that we don't always, when we're adding an item to the hash table, we don't always just insert it at the initial hash position. Sometimes due to a conflict, we had to create a chain and insert it at a different position in the hash table. So if we are trying to remove an item from a hash table, there may be other items that had to basically probe over that position to be inserted into the hash table. So we need to consider that basically when we're deleting that item, anything between the current item and the next empty position or empty space in that hash table might be part of an existing chain. So we need to make sure that we can reinsert all those particular values into the hash table. So let's look at an example if we're doing just a bad delete. So in this example, we're going to delete this particular key at position 5. We remove it and we just delete it and leave it empty. Now if we search for Horowitz at position 5, you'll see that it gets a key error even though Horowitz is actually in the hash table. So what happened there is we actually broke the chain, and it meant that any items that relied on position 5 to find that particular item will no longer be able to be found. So we basically see as we search for that item in this bit of code in the linear probe, it would actually raise a key error, even though, like we said, Horowitz is actually in that hash table. So as a way of dealing with the bad delete where it just removes the item, what about we shuffle all the items back, so we remove the gap. So from n+1, we just move them back 1 squared to the basically first empty position. Is that a good idea though? Probably not, because just if we move them back 1 position, it doesn't mean they'll put into their correct positions. So let's look at an example again. So we again remove this key, we remove all the items back 1 position, shuffle them up, and we shuffle the items 1 back. And now if we search for Horowitz at key 5, we'll find it without problem. However, if we look for the next position, which was actually mapped originally to position 0, we'll see that we can't find it. It will go to position 0, it would then linear probe via 1 and 2 and wouldn't find the item. So even though we fixed one of the issues whereby it was put into its correct position, the other keys were moved from their correct position into incorrect positions. So shuffling can incorrectly move elements. So one possibility is if we find at n that we need to delete that element, we need to insert every item beginning from n+1 until the first empty position. In other words, we need to reinsert everything that is in the remaining cluster. It's time consuming, though should not be many. So if we've got sparse data, hopefully our clusters aren't too big, and this approach is actually better than having to reinsert all the items in the hash table. So if we look at how we might do this, so firstly we find the position of where we want to delete the item, and then we set it to none. We make sure that we subtract 1 from our count to denote that the item is no longer in the hash table. So in this example again, we're going to delete the item, and now we need to basically get all the next items that we've got in the cluster and reinsert them into the hash table. So that's firstly reinsert Horowitz. We need to get the item so that we can assign that to a temporary variable, which is going to be item. We then basically set the table position, so we set position 6 to none. And because we're about to reinsert the item into the hash table, and as part of the set item we add 1, we actually first need to subtract 1 to note that we've deleted an item, and then use the set item to make sure that we can then reinsert it into the hash table. And we can see that in this example it was reinserted into position 5. Just note there we are using the str. We know in this example that the items will be a string, but we wanted just to make sure that the key is a string. So we reuse our set item in this example. The syntax might be a bit weird, but again, it is using the square brackets to basically denote that we're setting an item in the hash table. And then after that, we simply need to probe to the next position. In this case, we're going to look at position 0 and do the same thing. So in this example, AHO, we're going to reinsert that key. So we're going to do the same thing. It basically gets the item and finds the new position which we're going to insert it. In this example, it doesn't move, but it's going to say at position 0. And then we add 1 to our position, so it's going to go to position 1 and do the same sort of thing. We're going to reinsert it, and we should find that it's inserted into the same position. We add 1 to the counter and do the same thing. In this example, we find that we actually reinsert this to position 6. So now we add 1 to the position goes to 3, and at position 3 we see that nothing is there, so we're done. We've actually reinserted all the items that were basically in that cluster or at the end of that cluster. And we know basically because of linear probing, and as we probe we only have a step size of 1, that the only items that could be affected as part of this deletion are items that are remaining in that cluster. So we're finished, so therefore we don't need to do anything else, and we've finished the deletion. So that's the end of the video on the first method on how we deal with deletion as part of linear probing. In the next video, we're going to cover another method of how we can deal with deletion and do a summary of conflict resolution.